Good morning, all people listening to our final webinar, the 5th webinar of DYNASTEE, Dynamic Calculation Methods for Building Energy Performance Assessment. Today is a somewhat special webinar where we can answer the questions that you have raised during the last couple of weeks. Before doing so, let me see if I can get my screen moved. Yes. I will introduce to you the panelists of today. There will be 8 people available for answering your questions. You see them named here. They have given the lectures from week 1, the 2nd of September, up to last week, the 23rd of September. You see them here, and you can raise the questions also to them. If you have problems with audio, look to these screens. We give you a minute or so to get everything organized well. Meanwhile, I will ask you if you have further questions that you like to have answers today. Please use the questions and answer box, and you may also decide to address your question to someone in particular. So make that clear in your question, but do not use the chat box, but use the Q&A box instead. All of our activities, they are recorded. They are available on dynasty.info. Maybe you have found out that already over the past couple of weeks. Also, we will continue using this website in the coming months for distributing documents, papers, or maybe data, or we will address to you more information about the upcoming events that DYNASTEE is organizing. So this is the last webinar of the series of 5 that we have organized in September. Today we have 2 hours available. We will give you a quick overview of what we have done and what we are supposed to do, and then we will also give more detailed information about the summer schools and the data that you can use. So we have addressed a lot of topics. Of course, these topics, they were all briefly addressed in the presentations. You can imagine that the presentations of 1 hour, they are really limited in comparison to the summer school, where we have a whole week available to interact with your questions and all the items that you are interested in. But during these 6 presentations, we have been addressing that we think are the most important topics that are dealing with the dynamic analysis for the building energy performance assessment. So we were addressing the building physics as well as mathematical models. We were supposed that you had knowledge about thermodynamic processes, everything that was dealing with heat transfer, and in particular the impact of solar radiation. So the complexity of the physical processes and how to translate that physical process in mathematical models, it is addressed by us. It's quite complex, and we have tried to increase that complexity a little bit. But you will find out that we are not really at the end of this complexity. We have been addressing briefly also how important is model simplification, how to get from a real building describing the building physics and how that is supposed to have the information in all the data that has been gathered by experimental activities. We have been addressing also the variability of the environments and the uncertainty of the data. And again, also here, we have addressed it only briefly. It is quite complicated in the whole process of data analysis. And also there, the summer school will be more informative. The same is valid for what it can be measured and what data is available, including the information, but also all the not measured phenomena. There are a lot of actions or behavior of the building that are very difficult or even impossible to measure. So we have also to deal with that aspect. And how do you put that in mathematical models, and how do you perform there the uncertainty analysis? What we have done also is make available benchmark data. And in fact, we have started that, and I will come back later to that as well, with simulated data, but we have made available also real experimental data. So these were the topics that we have been addressing very briefly over the last weeks. We have also said that in what you are in fact dealing with is a huge number of observations, and they are coming from time series, so it's a long period of time with a huge number of sensors that are supposed to describe or measure the physical processes. And the whole process of analysis has to do with what is the best and the most suitable method to arrive to valuable results. How do you get one or a few output data from so many input data, from raw measured data? That is more or less the whole question that you have to deal with. We have discovered over the last 25, maybe already 30 years, that you need to have more than only one disciplinary activity. So we have found out that building physicists are working really well with mathematicians and statisticians. And if they are working well together, then also the whole data analysis process works well. But what we have found as well is that you need really yourself to build a skill, a certain level of skill in order to perform well. So that is why we also like to emphasize that you need to have regular training and you need to challenge yourself, for example, in competitions or in new data, and to discuss this with colleagues and to find out if they have other ideas. So after 25 years, we have really made the statement that for dynamic analysis applied to building energy performance assessment, training makes really sense. That is our conclusion, and we hope that the participants are picking up this statement. So what we have been addressing as well, we have been discussing two methods. One is LORD. Paul Baker has given the introduction to LORD that was developed in the past. Peter Bacher, he has discussed and presented CTSM in the R environment, and in particular gray box models and continuous time models. And these two, they are more or less the methods that we are using most of the time for our analysis work. You can find in some of the documents that we have made available on our website, you can find more information, you can find more links to obtain more detailed information about LORD as well as on CTSM-R. So these two methods we have been presenting, and that is also that we will continue to do in our summer schools in the future. What we have done also is we have presented to you benchmark data, and the two highlighted are from homogeneous walls. One is simulated data that was distributed in the beginning of September. Then we have also made available 2 weeks ago the data from the round robin box that is still very interesting and very high quality data for all kind of different analysis work that you can do. And what we will make available from this afternoon onwards, we will make also a real in situ experiment, the data from it, from a homogeneous wall, that you can also check your skills if you are able to find more or less the best way to analyze that kind of data. So these 3 data series, they will be available on our website, and you can raise a lot of questions. There have been already in the past a number of participants. I think that for the in situ wall, we have over 150 people studying this particular situation. So that is all available for the participants. Here is a little bit more detailed description of it. The simulated data, there were 2 benchmark cases, 2 different ones. They are giving you the correct creation data, so you can test really your own skills to find that original design data. It's giving you also some description of physical definitions and statistical tests. Then round robin box data that has been distributed 2 weeks ago. It is 3 periods, 3 different periods, but you can make them as a long data series. And it is dealing with some volume. You have 6 walls. One is a window, so you can also do some analysis on how to get the thermal characteristic data of a window. It is coming with an instruction document where you find a clear description of the experiment, and you can find also all the descriptions of the sensors and instruments that have been used. That one is also available on our website. You can find here the 3 different heating schemes. So here is coming up a ROLPS. We come back to ROLPS a little bit later in the question and answers. The co-heating experiment, and we have a low set point heating experiment. So there is also a lot to play with for the analysis. You can also increase yourself the complexity. For example, you can only look to a wall to assess the thermal resistance of a wall, and to avoid the impact of solar radiation, you can start with the rear wall, and then you can look to other walls. What is then the impact of solar radiation? And of course, you can look into the volume surface situation by the severe analysis that has been presented briefly by Paul Baker in the first webinar. And then the in situ wall data that is coming today or tomorrow on our website, that is having 2 periods of data, shaded and not shaded data, and it is the average of 5 different sensors. It has a complete description of the experimental setup, and the data is also available on dynasty.info on the online training page. So that is about the all the information that we have given to you in the last couple of webinars. And of course, a lot of participants, they came up with questions. And these questions we will now try to answer to you. And I will start with the first one. Please, could I have access to the large software? Maria Jose is there to answer that question, as well as the next one on the summer school. Maria Jose, can you give information about it?
Yes, it is possible. LOR is free, so you can access to it. Just send me an email, and then I will give you the software and also the user manual. I think my email is in the list of the presenters, in the list of the lectures. And then about the summer school, yes, it is postponed to June next year. And we have afterwards some slides with more information about the next edition of the summer school.
And then we will address also if participants, yes or no, can receive the credit points for PhD work.
Yes, by now it's not possible, but they will have a certificate of attendance, including the topics, the hours, the date, and all the information about the training activity they have followed. It's a kind of certificate that they have followed this activity.
Okay. Another question that we already received in the very beginning, how to estimate the thermal capacitance of a wall. Paul Baker, can you answer that question?
Yes. I think the easiest way is we've had an email exchange with one of the participants, but to answer this simply, I think is difficult at this moment. But we will prepare a document showing different approaches to the calculation of the capacitance of the wall, and that will be put on the website in due course.
Yeah, and maybe I can also that might be available in a couple of weeks, since we have already prepared a kind of a starting document, and we will elaborate that, and we will come back to it in a couple of weeks and place that document on our website. And that is also that I will answer this, that some people, they were interested in an article on PRBS and RollBS. There was circulating already a short document on PRBS. RollBS is somewhat derived from PRBS. I will elaborate that article as well, and we will put it also in a couple of weeks on our website, a little bit more elaborated in the sense that it is becoming clear also to the normal reader of an article. For the moment, it is just a document with some notes and some links to external articles. So we promise that will be available in the coming weeks. And then we had also it was very nice to discover that people in Brazil were also following our webinars, and they made us aware of the time zone that they were in. And when we were starting 10 o'clock, I think it was 5 o'clock for them in Brazil. But meanwhile, we have made it available, all the recordings of the presentations. They are available on video, and you can find them on our website. So these people were happy as well, and I hope that they are still happy, and they may join us also later and come forward with questions. Then I give Aitor. You can briefly reply to the questions raised after your presentation. So can you give briefly an answer that you were giving then?
Sure. Thanks, Hans. So these 4 questions, I already answered them during the webinar 3. I think I answered them quite precisely, but about question 1, realistically, how precise can you expect to model a real building? That's a very hard question, but the more precise measurements you get from the real building and the more signals you measure, it's possible to get models with a higher precision. But the idea would be to get parameters that are able to characterize real buildings, such as heat loss coefficient, equivalent solar apertures, or equivalent thermal capacities of real buildings that should be below a 10% of uncertainty. But that's a very hard task, and there are many research groups working on it, and there is even an annex of the International Energy Agency, the Annex 71, when there are many research groups dealing with these tasks. But you can read also the coheating method, that they are able to make some precise experiments to get the heat loss coefficients of real buildings when they are unoccupied. Yeah, and they try to be there in the about a 10% of uncertainty of the estimated parameters. Then about question 2, how do you choose the position of the sensors, temperature, CO2? Well, there are usually some general guidelines, but for each of the type of sensors, the manufacturers usually give them. If you are going to install wattmeters, they give you the connection schema for the wattmeters to be installed in the electrical boards of the buildings. When you install calorimeters in the heating systems of buildings, you usually have to install them. You install the volumetric flow meter in the return, and then you install a temperature sensor in the water in the inlet, and another temperature sensor in the return, and then you make a conversion of the volumetric flow rates to mass flow rates, and you have mass flow rate multiplied by the specific heat of that fluid. Usually it's water, or water with some glycol or some type of fluid, not to get frozen in case of there are tubes in the exterior. And you get from the manufacturer how to install it. And then it's more complex for the sensors measuring comfort parameters in interior thermal source of buildings, such as temperature, relative humidity, CO2 concentrations. And in those type of sensors, you have to install them in a representative place of the thermal zone you want to get the measurement. Of course, the bigger the thermal zone, the harder to have a place where you get a representative value of the temperature, CO2 concentration, and relative humidity of the thermal zone. But usually, the position in the indoor of this type of sensor should be in a wall that is not in the envelope. It must be an inner wall where you have no direct solar radiation striking in the sensor. There are no air currents passing next to the sensor, and it should be in a height of about 1.5 meters. And for the outdoor air temperature, outdoor CO2 concentration, outdoor relative humidity, you have to be careful that installing the sensor shielded against solar radiation and in a place that usually is the roof, if it's possible. That's usually the best place to get measurements of this type of measurements in the exterior of the building. For question 3, if the heat transfer through thermal bridging can be the 50% of total transmission heat loss, why are these ignored? Yeah, I think I answered this question, but when you make energy, you don't ignore them, because if you characterize real building based on real monitored data, when you measure the heat input to the building, that heat input is partially lost through the one-dimensional heat transfer building envelope components, but part of that heat is also lost through the thermal bridging. So when you make energy balances of the building, of the whole buildings, you are actually considering the thermal bridges within the parameters you estimate in that building, such as the heat loss coefficient. So we are actually not ignoring this thermal bridging using the techniques you are learning in this course. And finally, question 4, are there sensors that calculate the thermal comfort levels of a building according to a specific model, or we have to calculate it by collecting each parameters? Well, I don't get this question perfectly, but the thermal comfort levels are usually are related to the indoor conditions of the thermal zones you are monitoring. You usually monitor indoor temperature, indoor relative humidity. Those are the two main parameters related to the comfort. Then there are also parameters related to the air quality, such as the CO2 concentration, that gives you a very good information about the ventilation system in that thermal zone. If the ventilation is not enough, the CO2 concentrations will be too high. But for the comfort part, you usually have in the ASRAE documents some specifications that permit you to know if with a certain temperature and a certain relative humidity and a certain activity level, if you would be in a comfort zone or not. So actually the sensors don't calculate you directly the thermal comfort level. The sensors measure temperature and relative humidity, and then depending on the activity level and the time you would be using in that thermal zone, you will calculate if the 95% of the people or 80%, depending on your analysis, a percentage of the people using that thermal zone would be in comfort conditions or not. So I think that's the answer to these 4 questions. You also have the answer to these 4 questions in the webinar 3 videos, so you can check them also, the answers there.
Okay, thank you. Then we continue with some questions that were raised to Irati. Irati, can you also briefly repeat a little bit the answers that you were giving to these questions?
Yes, of course. I also answered the questions the other day, but well, maybe to understand them better, I will repeat them. So what does medium mean in the model formulation? How is it different from the interior? Okay, when we simulate a wall, we consider there are hypothetical layers like between the interior and the ambient. In order to make the models estimate the parameters these layers could have. No? So then the medium is not a real layer. and we don't have measured data for this layer, for this point. No. However, what we can make is to make the models estimate the hypothetical temperatures this point could have and check if it's reliable or not, comparing it with the rest of the temperatures and the location of this point. And then, so the medium could be a layer between the interior, in this case, and the heater, and we could estimate the hypothetical temperature this point could have. But it is not measured and nothing like that. It's only to compare with the rest of the measured values and to check if it's okay. And then the second question, it's related with the weights, I think. And why is the weighting parameter needed in the simulation? Can different persons get the same results for the weighting parameter? Okay. Yes, in this case, if you remember the other day, I told you that it is only used when the models are not able to get good residuals, and this can happen because the switcher is having a lot of movement or different behavior. So the weights are included in order to make the model behave differently when the heater is switched on or switched off, because after this moment, it is complicated to model this data. And then when we include these weights, what we do is to increase the level of the noise and to reduce the weight the data have at this point. Yes, and the next question.
Why?
Okay,
why
thank you.
use the data set?
Yes. Okay. Why reduce the data set to 3 days? Would the results be saved if the whole data set was used by minutes over 1 month? Well, in this case, I also told you during my presentation that I try to model the data in different ways. First, I start using the whole data set, using minutely data. Then, since I was not able to make it converge or to obtain good results, I changed it to hourly data. And then, since I had the same results for that, I reduced it. So, it doesn't depend. I mean, the modeling depends always on the data. If there are some problems to model the data, you are not able to obtain good results and residuals. So you have to start trying yes, trying different models, different ways to obtain good results. For example, you can also include the part of the weight I told you before, because maybe it's a problem related with the heater, or can be also a problem related with the limit we have put to the parameters for being estimated. So it depends. For a lot of things. So my recommendation is to try and see if you are able to obtain maybe results first with the minutely data, and then the key is to try modeling the data with different manners and see which one fits for you. And then I think the rest of them are already answered. That I think you already have the presentation and also the data set. So thank you. Okay. That's everything from my part.
Okay, thank you, Irati. Then we continue with the questions that were raised to Peter. Peter, I give you the floor to give briefly the answers that you were giving during your presentation.
Thank you, Hans. I'm standing solidly on my own floor at home, but I can maybe come and dance on your floor someday. But I can try to answer some of these questions. And the first 5 here are the ones that were also raised during the last week's session. But just to summarize, I think that it really, I mean, depends on the two first questions. Should we aggregate and so on? Again, my answer is really, it depends on your application. So which kind of information are you, can you use or do you need? So if you're interested in, let's say, the steady state characterization, so the heat loss coefficients and GA value and such, then, and depending on your data, then of course, to some extent, if you have enough data, then do average values and use this energy signature or like linear regression model and simplify it. That simplifies the model. So so basically, what kind of information are you interested in, and then don't make more complicated models where you need to model a lot more than actually what the information you're interested in, in order to obtain that. But of course, if you need to have a model for control applications and you need really the dynamics, then of course you need to model on the data that contains the information about the dynamics. So maybe on a finer time scale, like hourly or so. But by averaging, you can really remove complicated phenomena and you can simplify the model that you need. So that's the balance in some sense. Yeah, I mean, in a sense, we can talk about the first, on the other questions. I think it links to this. It links to the last two questions up here. At least regarding the noise and especially the model selection. I mean, which type of models should we use? Okay, let's say we decided to use the ARX model. That's what we suggested in this Annex 58 statistical guidelines as a fundamental procedure. And we suggested how to automate also to model, to verify the model. I'll just share a link in the chat box so you can open, or in the Q&A box, maybe, just not to confuse then. Oh, I cannot post anything on the Q&A box somehow. I think I can post this link in the, okay, I didn't check this. I think I can post it in the chat. So now I'll send you a link in the chat box, so if you can look at that. Then it's the outcome of Annex 58 is the reports are available on this website. And you see under subtask 3B, you see the statistical guidelines, and if you press on that, you get a PDF file. And in that, I mean, I don't know if you can all open that right now on your computer, but there is on page 31, there's a suggested model validation procedure, which also includes a model selection. So the basic idea is to say, use the first order ARX model and then increase the order, so include more and more lags until you obtain the white noise residuals and until the coefficient estimates p-value, so whether they are significant different from 0, until this p-value is too high, so usually about 5%. But so start with a simple model and add more lags until you obtain the white noise. That's, I mean, kind of a simple procedure to, and robust, which should be quite simple to automate and thus create a simple automatable way to select the model, the ARX models. And actually also for this report, there are also data and scripts with the examples of different applications of this. So you can obtain the data and the scripts for doing this. the examples that are in these statistical guidelines. Yeah, so the second question under other questions, how to interpret and incorporate model errors, sensor data errors, manufacturer errors, uncertainty on physical values, and so forth. And that is really, I mean, I mean, nothing is simple. So that's where we have to make some kind of compromise. You can say, in a sense, regarding model errors, you can say that's what the statistical model selection is there for. That is to choose the best model for this particular data. So in a sense, you will avoid model errors in a sense. But we know all models are wrong, but some are better than others for this particular application. So in a sense, you have to, I mean, that's always a compromise when you do statistical modeling. That is the model will never be perfect. So you will have to choose a suitable model. That's what we call it. So for this application, for this data, this model is the most suitable model. And that's what the model selection procedures are basically there for. Sensor data errors. Well, of course, you can say in the statistical models, that's exactly what we need to model. All the statistical models, time series analysis model, include a description of noise. And what is noise? That is basically, or error, that is basically something that's completely random that we cannot explain, at least with our available data. So in a sense, a statistical model includes the description of sensor random noise from sensors. That's exactly what it does. So if you can explain all patterns, you're just left with pure randomness, then you can say in a sense, that's originating from, for example, sensor data errors, or that's actually what's described there. However, of course, there can be systematic errors. So you can say, I mean, bias in sensors, they will create real problems. If you think that this represents the indoor temperature, and it does not, because there's a bias. There's like, I don't know, maybe you put the sensor in the wrong place, or then this will affect your estimates, and that's really difficult to correct for. I mean, that's impossible to correct for. So that's sort of the downside of using data. If they're inherited, I mean, basically, if what you think that the data represents is not what it represents, then you will make a bias or a systematic error in your estimates. But we have to live with that. But of course, we can sometimes say, okay, if you get these estimates, then it cannot be such that this is the indoor temperature. It's way out. So in a sense, you can of course check for things like that, but you can never make it perfectly in some sense. And then what's the most important things to mention in a report? And I think basically, especially when we have a data set, okay, Maria, the link is not opening. Oh, yeah. Okay, sorry. It's someone who asked that the link, I think you have to copy it into your browser to open the link that I sent in the chat, but sorry. So what's important to include in a report? I think, first of all, you will make a section about the data, and I always recommend to have a full plot of all the data. I mean, though you cannot see that many details if you have a whole year of data and you have measured, I don't know, it can be many variables, 20 variables, but at least some plot that contains the full information of the data where you can see if there are outliers and so forth. So just plotting the full time series in some way and include that information is very important, I think. So the reader can see somehow all the data, the entire data, and then of course zoom into some of the interesting or important aspects of this data. So you, because you work with the data, so you learned what are the important things that I learned from working with this data. And then you have to report that to the reader of the report. So, but it's kind of a creative process in some sense, and it's not easy because different people have different backgrounds and different objectives when reading a report. So it has to be some kind of compromise. But yeah.
What I wanted to say is that in LORD there is the error propagation tool available. So, Aitor, can you reply to this question?
Sure. Okay, so we received this question from Dayar Alan. It's when dealing with real data, real life occupied homes, there are unknown parameters such as solar gaze, metabolic internal gaze, infiltration ventilation, or air change per hour or hot water use. Can the uncertainties be quantified, estimated? If yes, how? Or are they predefined as for example, in Annex 58 or 71? Well, if we had answered to all this, there would be no research lines on this topic of modeling occupied real buildings. But the idea of the methods is that probably you are not going to be able to measure accurately all these phenomena. You are not going to be able to estimate solar gains accurately. You can measure in CO2 concentrations, relative humidity, or even combining them with techniques for estimating how many occupants you have in a thermal zone by artificial vision analysis. You can get the occupation of a building and even the metabolic heat rates with an accuracy of, with an uncertainty of 20%, more or less. You can get the other internal gains. This is all the electricity consumed within the building envelope is actually heat gain within the building envelope. Those can be measured quite accurately. And then the infiltration ventilation, the measuring infiltration is a very hard task. Ventilation is easier because if it's a mechanical ventilation, you can measure volumetric mass flow rates entering and leaving the ventilation system quite accurately. So the idea of the hot water is also possible to measure accurately. And if it's not in the energy balances, when you measure the energy provided to the hot water, if you are not considering it as a heat gain as a heat gain within the building that would be lost through the building envelope and will enter in the energy balance equations of your model, you will not consider it. So the idea is you have to find, when you have your data, the most certain data files. You have to introduce them in the model, and you have to try, if you are designing the experiments, you have to try to measure as accurate as you can the main heat gains within the building for your model. Because probably if you are working in winter in very cloudy periods and it's cold and rainy, solar gains will be really small. If those periods that you are analyzing are also very cold, probably the metabolic heat gains would be very small compared with the heating gains of the heating system that can be measured very accurately. So you have to try to analyze the building. This is one option in periods where the very uncertain signals, such as solar gain or metabolic heat gains, that are not measurable accurately, you know that their weight in the energy balance are very small. Other techniques, such as the dynamic methods that you are learning in LORD or in CTSM, in R, is that when you are modeling, you will let the model to identify those solar gains or even the metabolic internal gains. So anyway, in all these methods, there is a way of introducing the uncertainty you have in each of the measured signals, and each of the methods, LORD, CTSM, or averaging or regression method, will be able to expand this uncertainty to the estimated values. So if you have a big uncertainty in one of the signals that is very important for estimating a parameter such as the heat loss coefficient, then the uncertainty of those estimated heat loss coefficient would be very high. So you have to deal with two things. First, try to have as accurate data as you can, and very important to know the uncertainty level of each of those signals. And then once you decide the method for estimation that you will use, average method, regression method, dynamic method of lab parameters such as the LORD method or the CTSM method, then you will have to know how to introduce those uncertainties of each of the signals to be expanded, to be propagated to the estimated values. So that's the idea of dealing with the uncertainties on very hard measurable parameters that are quite common in real life occupied homes. I hope this answers you, but it's a very deep question.
Yes, but I can also add that, of course, when you have, let's say, smart meter data where you have maybe only measured the heating, and then you can have some challenges, of course, because you're not measuring these particular inputs. So, I mean, I'll just share again one link here, which is, I think, a paper which now eventually the outcome of Annex 71 should be addressing some of these issues. But I have here a link to a paper which just Christopher recently did. It's also working in Annex 71. And it's a, I think you can open it. So it should be available. You can view the full text or download the PDF. And eventually you can see that's like an energy signature model where it's a regression, but it takes care of the transition to summer period when there's no heating in a clever way. And eventually it's sort of, I mean, the question here is also, what do we do when we do not measure the internal temperature, for example, and thus internal gains? Eventually in this method, this not measured, let's say, heat inputs, in a sense, if you have just random behavior, that can affect the whole thing. But of course, if you had, say, an unmeasured external heat source, that will change the results. But here, when you estimate, we call it a base temperature in this paper, and it's basically the temperature at which includes all the unknown heating sources, and thus in the end also the estimate of the internal temperature. which we then call the base temperature. So that if you have a lot of other heating sources, let's say, then it ends up in that you would basically have a lower base temperature because it shifts that. But the UA value estimate will be, for heat loss coefficient, should not be affected by this. So there are ways to deal with that. Another interesting paper which presents a way to deal with solar radiation, solar gains, in a way where, I mean, usually we have measured the global horizontal radiation. However, at least if you go down to, let's say, hourly values, you will have clearly that just multiplying the global radiation with the coefficient is not what's entering the building. You will have some functional relationship to where the solar sun is, the position of the sun. So if it's morning, it hits the windows and enters in one way, and if it's the mid of the day, the position of the sun is different and enters in another way. But we can actually model such unknown functional relationships with smooth functions using what's called splines. So it's presented in this paper. So you can take a look at those techniques. And finally, the question is, can we do something about if we have not measured separately the heating for domestic hot water and space heating? And we did something on this where it uses like 10-minute values, so you have to have a rather high resolution for this technique, but it's a way to separate the spikes from domestic hot water from the more slowly moving space heating. So maybe that can be useful to look into for some applications for you. Yeah, and the final two questions. Depends. I mean, I don't think that they will fail. Most real data, we can make models where we have white noise. So I think that, I mean, depending on the application, but of course sometimes we cannot find the fully suitable model, so we will have to live with something which has some autocorrelation left, and it depends on the application again, and then the magnitude of the residuals and so. But I mean, yes, sometimes we have to make a compromise, but we can still use the models and for different purposes. But it's a difficult question in some sense. Yeah. So, and the last question, I'm not fully sure. I mean, if we can relate the parameters to a physical quantity, let's say the heat loss coefficient, then we should, of course, be able to compare it across different models using different data. Or, of course, if you have different sized building, you have to do something. Maybe you have to scale the values with the square meters or something like that, in order to compare across different buildings. But I mean, you have to relate it somehow to uninterpretable physical quantities in order to, of course, be able to understand how to interpret it and how to compare between, let's say, different buildings and so.
Maybe we can add that it also the requirements of reporting set by the directive, the buildings directive, and the performance of buildings directive. What is exactly requested there as a kind of a reference to each building? So if you want to compare it, you might look into a legal value that is used for example, for heating energy demands for space heating. So it depends a lot on what the requirements are for reporting. That's what, if someone has to add something to this last question, please help us. Otherwise, we move on.
Yeah, thanks for the questions. They were very, very good, clever questions. So, I mean, we have to work on this together and slowly agree on ways to deal with this. But I mean, I think we have a lot of applications and we have a lot of data, so we can use it for many useful things. But it's also a challenge to agree on how to do this in a similar way, or a standardized way.
Okay, we move on. There is. Oh, my system is stuck. Oh, wait a moment. Yeah. So we have now all the questions. Maybe more questions are coming in on the questions and answer box. I cannot see them yet. I don't know where to see it, but meanwhile, I give the floor to Maria Jose. Please inform us a little bit about what the situation is in organizing the Summer School 2021.
Yes, thank you. Well, the situation is that we have delayed this year's edition to next year. It will be in June 2021. And it will be in Almería, in the south of Spain, from the 16th to the 23rd of June. And it is a very nice place near the coast. And there, the idea is to give more information and more in-depth lectures about a bit more advanced level, and also go further in the study of the impact of solar radiation, for example, wind speed, etc. And in general, it is the target audience will be the same as the target audience that we have had for this online training. It is about dynamic calculation methods for building energy performance assessment. And we hope that this will be useful for continuing training on this. It will have two parts. The first part will be the last days of a week for 3 days. We will start with lore and discrete time models. Then we will have a weekend. During the weekend, you can study the topics that you have learned the days before, or just have some holidays or some touristic visits for the environment that is very nice in the south of Spain. And you can go for the second part, for the second week, that is the first 3 days, to go more in depth, working on CTSMR and continuous time models. So it is interesting that participants are already a bit trained on this tool. So this is very useful to get more in depth and to be more efficient in the learning. With I think that this first training activity that we have had these days will be useful for you to follow and to be more efficient in the learning in this summer school that we are proposing for next year. So we will have more information on the DYNASTEE webpage, and if you need more details, you can contact us for more information. So thanks.
Okay, then before we move on, I would like to give the floor a moment to Richard. Richard, maybe you can give us a little bit information about what we are planning to do in the coming years concerning the webinars or concerning the summer school, in what direction we would like to go.
Thanks, Hans. So we've talked a lot about modeling data and working with real data. I think the work of Annex 71, as Peter has mentioned, the outputs of the Annex will be very useful to guide some of the questions that have been asked today, particularly in terms of uncertainty, data analytics, and how we work with smart meter data in particular as well. So we have a session in April. So the date will either be April the 22nd or the 23rd of April in 2021. That will be held at Salford University in the UK. We will probably live stream that event, given that the COVID crisis might not have entirely finished by then. We'll live stream it or we'll capture it and issue the video on YouTube. But I think that will be quite interesting and will hopefully provide a great deal of input. And the outputs of the Annex obviously will be available to download as well at some point. So I think they could be very useful for researchers and also industry in this area as well. Does that sum it up, Hans? Do you want me to add anything else?
No, I think this is okay. What I can add is that we will keep informing the people using the website of Dynasty, but also that the platform of Annex 71 can be used. So that I think that's for the moment, and I will say that we will continue in providing information to the participants. Let me see if I get to this is the last slide where you can find a lot of information on Dynasty. You can go to the Data Analysis Online Training page. We have put there the data that we have presented in the very beginning, the simulated data. You can find also the data, including all the descriptions of the data series of the round robin box. You can find it as well. And later today or tomorrow, we will put there a third data series as well. So keep in contact with us. I need to go now to Valerie or to Maria to see if there have been any questions arrived during the last hour. I cannot see them.
We don't have any questions.
Okay, so that's good. Then I can only remind the people, if you have problems in using the data or if you have further questions, do not hesitate to send them to us. We will collect them and we will try to answer them also in the coming weeks. If there are no further questions, then I think that on the behalf of all the people, of all the lecturers, I think we have to thank all the participants for attending over the last 4 or 5 weeks all our webinars. Thank you a lot, and from my side, I say goodbye and hope to see you maybe at the summer school or maybe in April at the Salford University. So again, thank you very much for your attention. Thank you also to all the lecturers making available the time and the answers to the questions that were raised. And thank you also, Maria and Valerie, for assisting during these 5 weeks of webinars. Thank you very much. Hope to see you. Goodbye for now, and thank you.